Welcome to this course on nanostructured materials, synthesis, properties, self assembly and applications. Today we are going to go through the second lecture of module 3. We earlier have finished module 1 and module 2, and now we are in module 3, and today is the second lecture. The first lecture of module 3 we discussed about fullerenes, that is carbon based materials, C60 being the common fullerene and other fullerenes which were discovered from in 1985. Now, today we will start on carbon nanotubes and how the carbon structure in C60, which is spherical. Now, we get cylindrical structures of carbon atoms by rolling a graphene sheet. So, the previous lecture we saw clusters of carbon like C60, C70, C80, C82 etc. However, now we are going to discuss how to get cylindrical objects which are called carbon nanotubes and which has a relation to the C60 structure. Basically, they are all made up of carbon, and in C60 structure you had hexagons and pentagons of carbon forming a cluster. The number of pentagons are 12 in all carbon containing fullerenes. But the number of hexagons changes depending on the total number of carbons in the cluster, that is the total number of vertices, and this was given by the Euler's formula. The discovery of C60 led to the Nobel Prize to 3 people, Kroto, Curl and Smalley, which was given in 96 and it was discovered in 85. Now, the carbon nanotube was seen first by Ijima, and now we will discuss how you can actually get the carbon nanotube. Basically, you start, if you think of a graphene sheet. So, if we roll the graphene sheet, we can get carbon nanotubes or CNTs. Now, what is this graphene sheet? You must have heard of graphite. Graphite has layers of carbon, hexagonally arranged carbons or hexagonal rings of carbons forming layers or sheets, and these sheets are connected by van der Waals forces, weak forces, to form a pseudo 3-dimensional structure where the interactions are stronger in the 2-dimensional plane and weak in the 3-dimensional plane, that is graphite. If you take only one layer of graphite which is only having carbon hexagons of carbon like shown here, then that is called a graphene sheet. Now, this graphene sheet if you take and you roll it. So, assume that this graphene sheet is like a piece of paper and then you roll this graphene sheet, then you will get a cylinder, and that cylinder will then be called a carbon nanotube. But rolling the graphene sheet can be done in several ways, and depending on how you roll it, you will get different types of carbon nanotubes. So, for example, we define a couple of things like what is the chiral angle. That means, if you are connecting one line here and you are rolling it at an angle which is theta. So, that angle is called the chiral angle, and the chiral vector is defined using two unit vectors a 1 and a 2 like which are shown here. So, if this is a 1 and this is a 2, based on a hexagon you can define these two vectors, and then if you change the number of the coefficients. So, if n is say for example 2, then the length of this vector will become twice of this vector, and if m is 3, then m will be thrice of this vector, and then you have to get the resultant vector. The chiral vector will be the resultant vector, which will be the sum of n a 1 plus m a 2. So, what is depending on these numbers n and m, the chirality is defined. So, here is an example. This is a general vector, the definition which we gave with n a 1 and m a 2, but if you take a particular value of n and m, for example, if you take m equal to 0, that means this vectors, the chiral vector c depends only on a 1, that means it will be in line or planar to the a 1 axis. So, in this figure a 1 is denoted by this vector and a 2 is denoted by this vector. So, if m is 0, then this a 2 vector will not contribute to the overall chiral vector c vector, and the resultant will be always multiples of this vector a 1, and so it will be parallel to this direction, and that is what is shown here, that for a value where n is non-zero and m is 0, then the resultant vector will be along this direction, which is parallel to the a 1 direction. And if this is your vector, that means by this vector you are rolling the graphene sheet, the resultant carbon nanotube that you will get will be called a zigzag carbon nanotube. And if you take a general vector, suppose m is not 0, non-zero, then you will get some other chiral vector. Suppose both n and m have the same value, that means you take twice the amount of a 1 and twice the amount of a 2. So, the resultant will be like shown here, the resultant will always go through the hexagon, through these vertices and the edges, and when you roll this structure along this axis, then you will get what is called an armchair carbon nanotube. So, these coefficients n and m are very important in understanding what kind of carbon nanotube that you will get, whether you will get a zigzag carbon nanotube or a armchair nanotube or a chiral nanotube. So, any other value for an armchair, the chiral angle is actually theta. So, if n and m are same, then always you will get an angle theta, the chiral angle will always be 30 degrees, and for a zigzag carbon nanotube the chiral angle will be 0. So, in between 0 and 30 degrees, if you have any chiral angle between 0 and 30, you will have chiral nanotubes. So, this is what is shown here, that if you have theta, the chiral angle is equal to 30, you will have the armchair kind of structure for the carbon nanotube. So, m and n both are same. So, it is 5 5. So, one of the vectors a 1 is 5 times a 1 and the a 2 vector has a coefficient which is 5, and the resultant will be having this structure which is called an armchair type of nanotube. And if you want to close this nanotube, at the end you must have a structure which is related to the C60 structure. So, to close an armchair nanotube, that means m is equal to n kind of nanotube, you will have to close it with a half of a C60 molecule. So, half of the C60 here. However, for other nanotubes, to close the nanotube, the structure has to be different. So, for example, this is a nanotube where m and n are not same and n equal to actually 0. So, the chiral angle is 0 and this is the zigzag form of the nanotube, and in this nanotube, to cap the end of the nanotube, you need a structure, you need a Fullerene structure which is not the C60 structure, but is actually close to the C70 structure. So, the C70 is this kind of molecule, and if you take half of it, you can close the end of this nanotube. So, depending on the type of nanotube, the type of the cap will also be different. Now, this is a nanotube which is neither an armchair nanotube nor a zigzag nanotube. That means, the chiral angle lies between 0 and 30. So, the chiral angle will be between 0 and 30, and this will be a chiral nanotube, and for a particular value of m n. So, 10 and 5. So, neither they are equal to each other. So, it is not a n n or a armchair type of nanotube, or neither one of the vectors has a 0 coefficient. So, it is not a zigzag nanotube, but this is a chiral nanotube, and for this particular nanotube, to close the end of the nanotube, the structure that you need is different than what you need for this nanotube and this nanotube, and if you calculate, you will find out that this end can be capped by a fullerene which has 80 carbon atoms, and if you get that fullerene and divide into half, then that hemisphere, although it is not a true sphere, it is a kind of expanded sphere, that half of that will be capping this nanotube, which is a chiral nanotube. So, depending on the n and m values, the coefficient of these two vectors by which you define your chiral vector is very important to know what kind of carbon nanotube that will result from a particular kind of chiral angle. Now, what are the properties of such carbon nanotubes? They are very important, and there are many kinds of properties which are better than existing materials. For example, the electrical conductivity, that is the ability to pass current, is 6 orders of magnitude higher than copper. All of you know that copper is a very good conducting material, and so we use copper wires in all our electrification, and it has a very high conductivity, that means very low resistivity. Now, if the conductivity of copper is say around 10 to the power 8 ohm meter, then the conductivity of carbon nanotubes will be 6 orders of magnitude higher, that means 10 to the power 14. So, it is tremendously high electrical conductivity compared to normal materials like copper or aluminum, which are used to conduct electricity. Not only that, the carbon nanotubes can carry very high current. That means, if you compare a wire of unit cross section of copper and carbon nanotube, the carbon nanotube wire can carry much higher current than the copper nanotube. Then another important property with respect to electrons is that if you apply a potential or a voltage to carbon nanotubes, you can get electrons out of it. So, it is called a field emitter. That means, if you apply a electric field, you can get electrons out of the carbon nanotube. Now, there are other materials which show this effect and are used in many applications. These particularly there are compounds like lanthanum hexaboride or tungsten metal, which are also field emitters. That means, if you apply a potential electric potential, they will release electrons. So, they will emit electrons. Now, carbon nanotubes are excellent field emitters, and that is because they have very high aspect ratio. The aspect ratio of any wire or a rod is the ratio of the length divided by the diameter. Now, if you have a very high aspect ratio, that means the length is very high and diameter is very small, that means you have a very high aspect ratio, and you will have a very small tip radius of curvature. Now, these facts, that high aspect ratio and small tip radius of curvature are very useful for field emission, and hence carbon nanotubes are very good field emitters. Now, there is another property of carbon nanotubes, that you can functionalize them. That means, you can do some chemical reactions on the surface of these nanotubes, like you can put carboxylic groups or many of the groups that you study, amino groups, etcetera, on top of the carbon nanotubes. Once you functionalize them, you can do several other type of chemical reactions with carbon nanotubes. So, these are some of the very important or key properties of carbon nanotubes. Now, coming again back to electronic properties, which we said that they are very good conductors. The reason is that it has nanometer dimensions. The carbon nanotubes are having diameters in the nanometer regime, and because they are made up of a rolled graphene sheet, and graphene itself has very unusual properties. We call that graphene is a Dirac solid. It shows ballistic transport, that means very high conductivity. So, since carbon nanotubes are made up of graphene sheets which are rolled into cylinders, they have unusually high efficient electronic properties, and due to these two factors. The carbon nanotubes of course, will depend on their structure, and their structure depends on the chiral angle. So, the chiral angle and the coefficients of the vectors which we discussed, the n and m values, will be very important to determine the electronic properties of the carbon nanotubes. Now, we all know that graphene is a zero gap semiconductor, whereas carbon nanotubes can be metals or semiconductors, and they can be semiconductors with different energy gaps. So, they can have low gap, high gap. We can modify the carbon nanotubes by changing the diameter of the carbon nanotube and also the helicity of the tubes. So, the helicity of the tubes depends on these indices, on the chirality or the coefficients of the vectors, which are the n and m values. So, carbon nanotubes can vary as metals, semiconductors, and semiconductors with different band gaps. So, in general, if you look at single walled carbon nanotubes, which are called SWNTs, if you have the coefficients n and n to be same for these nanotubes, then they result they have metallic conductivity. If you have the carbon nanotubes made with a chiral vector, where the coefficients of the two vectors a 1 and a 2 are n and m, and the difference between n and m is multiple of 3, it is like 3 j, where j is an integer, then the gap is very small. So, although it is a semiconductor, it will have a very small gap if these values n and m are related such that n minus m is equal to 3 j, where j is a integer. So, if n minus m is 3 or n minus m is 6, then the nanotube, the carbon nanotube will be a semiconductor, but with a very small gap, and for any other values of n and m, they will have much larger band gap. So, depending on these values of n and m, you can have metals, small gap or tiny gap semiconductors, or large gap semiconductors. So, to remember, you cannot graphene are normally zero gap semiconductors, whereas carbon nanotubes can have small gaps, large gap, and they can also be zero gap semiconductors. Now, the applications of single walled nanotubes has already been shown, and we have couple of them are mentioned here. The intermolecular field effect transistor was discovered or made using carbon nanotubes in 2001. The logic gate, intermolecular logic gate using single walled carbon nanotube was made in 2001 by IBM, and the details of this are given in this reference here, where first time carbon nanotubes were used to form an FET, which is a very important part of the electronic industry. Now, this has tremendous implications of making very small chips using carbon nanotubes. Now, from electronic properties, if we look at the mechanical properties of carbon nanotubes, they are also excellent. The carbon carbon bond in a graphene layer, in the graphene layer you have carbon carbon bonds to form 6 membered rings, and then these 6 membered rings are then connected to other 6 membered rings, and it forms a layer or it forms an extended system. Now, in any extended system, the carbon carbon bond in graphene has the strongest bond. So, it is the highest bond energy of any system compared to any other system is present in graphene. So, since the carbon nanotubes are based on a rolled graphene sheet, this property of this strength of the carbon carbon bond in an extended system will also translate into the carbon nanotube. So, carbon nanotubes are the strongest and most flexible molecular material because of this carbon carbon covalent bonding and seamless hexagonal network architecture. So, it is one of the strongest and most flexible materials. The strain that carbon nanotubes can take is like approximately 10%, which is much higher than any other material. So, the thermal conductivity, which is another property. So, you had the electronic conductivity, which is very high for carbon nanotubes. The thermal conductivity is also very high. It is 3000 watts per millikelvin in the axial direction, that means in the long direction of the tube. However, in the radial directions, that is along the diameter of the tube, the value of the thermal conductivity is lower, but this value of 3000 is extremely high, and this is present in carbon nanotubes. So, let us look at a table which gives you mechanical properties and compares the mechanical properties of several engineering materials or engineering fibers, and if you compare them, especially you compare the strength and strain of carbon nanotube with steel or other carbon fibers, polymers or glass and Kevlar, which probably I even mentioned in my previous lecture. You see this value of carbon nanotubes has a strength of around 10 to 60 gigapascals, and the strain is 10%, which we just mentioned, and there is nothing comparable in any of these materials which is close to what we have in carbon nanotubes. So, extremely good mechanical properties compared to all known materials which are used in engineering today. So, carbon nanomaterials, carbon based nanomaterials, especially carbon nanotubes, are better than other carbon based materials which have been in market, and polymers like Kevlar, which are already in market for bulletproof vests, etc. But you see carbon nanotubes has higher number even compared to Kevlar. Now, compared to now, if we compare the electronic conductivity and thermal conductivity with other materials, together we can call them transport properties, because we are talking of either movement of electrons or charged particles or movement of what is called phonons in thermal conductivity. So, if you look at carbon nanotubes, compared to other materials like copper or other carbon fibers. You see this number of 3000 or greater than 3000 is one order of magnitude higher than copper and 3 times that of a well known carbon fiber. The electrical conductivity is around 106, 107, and of course, this carbon nanotube it is not 106, actually it is 10 to the power 6 to 10 to the power 7, and it is very high compared to many other materials. So, these are order of magnitude higher than other materials. Now, what are the potential applications of carbon nanotubes? Shown you several applications, but there are many other applications of carbon nanotubes other than what has been shown here. Among them you can see you can make conductive plastics, structural materials because of its high mechanical strength, then because of its field emission properties you can make flat panel displays and several other applications which we will discuss in subsequent lectures. But the point is one single material like carbon nanotube has so many applications, and this is also a very small list. So, we will come to the applications later in our next lecture, but this was just to give you a brief idea that there are many applications possible. Now, coming to the synthesis of carbon nanotubes, normally the other forms of carbon, the other allotropes of carbon that we know like graphite can be made using ambient conditions, and in graphite, which is this is graphite. So, this is one layer of carbon with hexagons arranged, and this other layer of carbon is shown here. Like that, there are many layers of these hexagonal layers one above the other to form graphite, and here all carbons have sp2 hybridization to form these planar structures. Now, this can be obtained in ambient conditions, that means under normal temperature and pressure, whereas if you go to diamond, which is another allotrope of carbon, you need very high temperature and pressure, and the structure is very different. So, you know graphite has this layered structure and diamond has this 3 dimensional structure, where each carbon is bonded to 3 other carbons, and this each carbon is in a tetrahedral position. So, you can see, so it is tetrahedrally coordinated to 4 other carbons, and hence each carbon has a sp3 hybridization, and this structure is of course cubic, this is hexagonal. Now, so you see graphite can be obtained in ambient conditions, diamond can be obtained under high temperature and high pressure conditions. For nanotubes or C60 type of molecules, we need very specific growth conditions, and in both nanotubes and the other fullerenes like C60, C70 etcetera, the carbons have both sp2 and sp3 character, and then we get this cylindrical type of structures as shown here. So, this is a cylindrical nanotube, and this is a armchair nanotube, because you see n and m both are 10, and we know when n and m will be same, the chiral vector will show you, and you are rolling along that vector, you will end up with such a nanotube which is called the armchair nanotube. And in C60 of course, you know we have this cluster like the shape of a football, and these require specific growth conditions. Now, the finite size of graphene layer, that means, if you take a graphene layer and you are rolling it to form this carbon nanotube, why should it stabilize? That is one question. Now, this graphene layer has several dangling bonds, that means, the carbons in the planar graphene layer have some unsaturation, they want to bind to some, they want to take up some more electrons. So, they want to form some more bonds. Now, when you roll and make a nanotube from a graphene layer, that eliminates these dangling bonds, and that is a very kind of positive thing for lowering energy. When you are eliminating dangling bonds, you are stabilizing the system. Of course, because you are rolling the graphene layer, there will be an increase in the strain energy, but together these two factors will lead to a energy decrease, and hence the nanotube is formed. So, formation of the carbon nanotubes is basically driven by the need for the dangling bonds to find to make some bonding and help eliminate these free electrons or dangling bonds which will then stabilize the system. However, there will be an increase in the strain energy, but overall the total energy will decrease. So, to synthesize carbon nanotubes, several techniques have been designed over the last 10-15 years. The earliest technique, like the arc discharge method, was discovered in 1991. It is also called the Krashmer-Huffman method. Then the laser ablation method, where you use a laser on a target, a carbon based solid material, and then you vaporize the carbon, and then when it settles down, it forms carbon nanotubes. Then later CVD technique, which is well known for other materials, was also applied to the synthesis of carbon nanotubes, that was in 1993, and then high pressure carbon monoxide based synthesis, which is also called the HIPCO method, was discovered in 1999. There is another method which uses a cobalt molybdenum catalyst, and this technique was developed in 2000 for the synthesis of carbon nanotubes. The CVD technique is very popular when you want very large quantity of carbon nanotubes. Now, to describe the first two techniques, the arc discharge method and the laser ablation method, both involve condensation of carbon atoms generated from evaporation of solid carbon. So, you take a solid carbon source and then you evaporate it, either using a arc discharge or by laser ablation. Once the carbon atoms are evaporated from the solid carbon, then it condenses back to form this carbon based nanotubes. The temperature in these cases is close to 3000 to 4000 Kelvin, which is close to the melting point of graphite. So, it is a very high temperature process, but both produce high quality of single walled nanotubes and multi walled nanotubes. Multi walled nanotubes can be tens of micron long and 5 to 30 nanometers in diameter, and they are normally, the multi walled nanotubes are normally very straight, whereas single walled nanotubes can be very curvilinear, that means they need not be very straight, and they are normally produced in the presence of a small amount of a metal, and this small amount of metal, whether it is nickel or cobalt, acts as a catalyst, and that allows the growth of single walled nanotubes. That means, you have only one graphene layer forming the nanotube, whereas multi walled nanotubes you have several graphene layers, one inside the other, forming several cylinders, one cylinder inside another cylinder of nanotubes. So, the single walled nanotubes normally need a metal catalyst and is produced in the form of ropes, where there are several single walled nanotubes. They are bunched together and weakly packed through van der Waals forces, and they form a rope like structure, and they are also very curvilinear, whereas the multi walled nanotubes are normally very straight. Now, this is the arc discharge method, and this was the process shown here as developed by Ijima, and here you see the nanotube was first observed by Ijima in 1991 in an electron microscope, and it was made using this arc discharge method, where you have a cathode and an anode, and there is a deposition of the carbon nanotube on the cathode. So, you have the nanotubes on the cathode and also on the walls of this when you pass a high voltage on this on these two electrodes, and here also the temperatures are close to around 3000 degrees Celsius. Now, several catalysts are used, as we discussed: iron, yttrium, nickel, cobalt, molybdenum. Several catalysts have been tried, and sometimes mixture of catalysts are used, and so they appear to be better, especially when yttrium is used with some of the metals. Now, this arc discharge method, so is a high temperature method. This is a typical discharge which is taking place between the two electrodes, and the during this discharge, the which is between graphite electrodes you have, and then the deposit is on the cathode, and from that deposit you can extract the carbon nanotubes. Now, using laser ablation, which was developed by Richard Smalley at Rice University in Texas in USA in 1995. So, what he did was he took this graphite target. So, you take a piece of solid graphite and you use a laser beam on top of the graphite target, which is heated by a furnace. So, the furnace is around it. So, and it has a temperature of around say 1200 degree centigrade. So, when this laser beam hits this target, carbon atoms are vaporized, and then they condense on a cold water cooled copper base and or collector, and carbon nanotubes deposit on this copper which is cooled by water. So, this is the laser ablation technique. So, like the arc discharge method, this is also a high temperature technique, although here temperatures are like 1100 to 1500, whereas in the arc discharge method it was around 3000 degrees Celsius. And the best yield you get is when you use catalysts with like nickel and yttrium mixed together, you get the best yield or quantity of carbon nanotubes deposited on the copper collector. Now, these are some of the pictures. These are transmission electron micrographs taken on arc discharge and laser ablation methods. So, this is the paper of Ijima in Nature, who first discovered the carbon nanotubes, and as you see there are multi-walled carbon nanotubes, and this is a single walled carbon nanotube. So, there is only one carbon nanotube as drawn here, and these are the schematic diagram to show you that this is single layer, these are multi-layer multi-walled carbon nanotubes, this is also multi-walled carbon nanotube, and this is by another group where you can see the single walled carbon nanotubes, which are connected to each other through weak van der Waals forces. So, there are several, it is a bundle of carbon nanotubes like a rope, they align themselves, and this is a high resolution TEM picture of these carbon nanotubes. Now, there are problems with these two methods. You always need to evaporate the carbon source, which requires high temperature, and then you need, when you get the material which is collected on the cold collector like the copper collector, then you need to purify it by using particular type of solvents, and there is need for alternative methods. Hence, the chemical vapor deposition, the technique was already known for other type of materials, was developed, and in the chemical vapor deposition you use hydrocarbons like acetylene or methane, and it is passed through a chamber where there is a substrate on which you want the deposition to occur, and there is a heater to heat the substrates. So, the temperature of the substrate is around 700 degree centigrade, and so what you are passing is the source of carbon. Here is a gas which is a hydrocarbon, and typically you use acetylene gas or methane gas for the carbon to deposit on the substrate, and when the carbon deposits on the substrate, it deposits in the form of carbon nanotube. Under these conditions, when you have certain catalysts like nickel, cobalt, iron, and the temperature is around 700 degrees, and the product yield is around 90%, and they are pure to about 90%. So, this is a chemical vapor deposition technique, where the temperatures, as you see, has been brought down to 700 degree centigrade, which was 1500 in the laser ablation method and 3000 degree centigrade in the arc discharge method. So, in a typical CVD method or the chemical vapor deposition, you have the hydrocarbon, you have the catalyst, and around 700 degree centigrade, and you get CNT. And the steps which occur is, first the hydrocarbon dissociates, and then it dissolves on the metal catalyst, and then it saturates in the carbon atoms in the metal nanoparticle, and finally, you reprecipitate carbon in the form of nanotubes. Now, here you can see a picture of the CVD method on a substrate. The substrate is porous silicon, and you are passing methane gas, and you have iron patterned on it as a catalyst. So, these are your silica, the porous silicon and you can see the aligned nanotubes. This is the side view of the towers, and this is the SEM image to show the aligned nanotubes. Now, how do these nanotubes form, these aligned nanotubes? So, you took a porous silicon, that means there is a silicon which has got particular pores, and in that pore, so you have this porous silicon, and below that of course, you have got the crystalline silicon, and here where you have got pores, you have got these gases will go in, and you have got this catalyst which is iron, which is patterned, and the growth will take place like from the catalyst particles. So, these are iron atoms. This is a blown up picture of this part, and you can see that where the catalyst particle is there, the nanotube is growing from there. So, this growth of these nanotubes on the catalyst particle is shown here, and so you need this iron patterned on the porous silicon to form these nanotubes. So, wherever the iron is there, on top of that a carbon nanotube is grown. So, whichever way the iron is patterned, ultimately you will see a pattern of the nanotube. So, that is how you get these aligned multi-walled nanotubes on a iron pattern over a porous silicon substrate. So, this porous silicon is important for the gas, the hydrocarbon to go in and interact with the catalyst, and then reprecipitate as carbon nanotubes. So, the carbon is first formed, and it dissolves in the catalyst, and then reprecipitates to form the carbon nanotubes. So, this is the growth process, and this particular mechanism where the catalyst particle is at the bottom and the nanotube is growing on top of the catalyst particle is called the base growth mode or the root growth mode. That means, the catalyst is at the base and the tube is growing on top of the catalyst. Now, there are several other new directions which have come about in the CVD process. We discussed the simple CVD. Now, there are several new methods where you can do selective growth of carbon nanotubes. For that, you need to do pre-treatment to provide selective deposition of the catalyst using photolithography. So, wherever you deposit the catalyst, you have to first modify the surface of the substrate by some pre-treatment, by which you selectively deposit catalyst, and then the carbon nanotubes grow on that. Then there is something called super growth CVD, or water assisted CVD to obtain well aligned forests. Here we mean forest by a forest of carbon nanotubes. It is not a forest containing trees, but it is a forest containing well aligned, that means each carbon nanotube is like a tree and it is aligned to each other to form a very uniform looking forest. Then there are other low temperature method developed, where you use a tungsten filament to increase the decomposition of the precursor gases. So, several new directions, but derived from the CVD or the chemical vapor deposition process have been developed in recent years. Now, coming to the next method, which is the high pressure or the HIPCO method, the high pressure carbon monoxide method. It was developed by again Richard Smalley's group in USA, and here what you have is a continuous flow of carbon monoxide. So, you have hot carbon monoxide from here, there is a furnace and you pass cold carbon monoxide with a catalyst, and this particular catalyst is what is called iron pentacarbonyl. So, it is a complex, a very well known complex of iron and carbon monoxide, and it acts as the catalyst here. So, in all earlier discussion also we mentioned that catalyst is important, but we were using metal catalysts like iron or cobalt or nickel or yttrium etcetera, or mixture of metals as catalyst. Here you are using a metal carbonyl as catalyst, along with that you are passing a cold stream of carbon monoxide gas, and here there is cooling water to make it cooler, and then here you have the furnace to heat this carbon monoxide. And by this method, which is called the high pressure carbon monoxide. So, the at high temperature carbon monoxide means the pressure is higher, and this will lead to the most stable single walled nanotubes. Like in other methods, the length of the nanotubes of single walled carbon nanotubes is very large, but to make small and stable nanotubes single walled, this technique is very popular, and the yield is also very high. You get 97% yield, and the purification yield is of course again 90%. That means, from whatever material you make, only 90% of pure carbon nanotubes, single walled carbon nanotubes you can obtain by this high pressure carbon monoxide route or the HIPCO route. Now, there is another method which is called COMOCAT method. This name comes because you are using a catalyst. This catalyst is made up of cobalt and molybdenum, two metals, and this mixture of metal catalyst if you take in this chamber and where you are passing carbon monoxide. So, you are passing carbon monoxide and you pass the catalyst here, and then it forms carbon dioxide. The carbon monoxide in the presence of the catalyst decomposes into carbon and carbon dioxide. So, the carbon dioxide is taken out, and that carbon which forms deposits as carbon nanotubes, and that is this is done at a temperature of around 700 to 950 degree centigrade. Now, this is also a very special method, because we use a very unique cobalt molybdenum catalyst, and this method is a good method because it does not form too many side products. So, it gives you very uniform carbon nanotubes. So, this is what is called the COMOCAT process. So, we have discussed various methods of synthesis of carbon nanotubes. So, this is TEM of the carbon nanotubes made by the HIPCO method, and you can see all this curvilinear form of carbon nanotubes, and by the COMOCAT method you can see much better quality of carbon nanotubes compared to the HIPCO method. Here you are using a catalyst of cobalt and molybdenum, and here you are using iron pentacarbonyl as a catalyst. Now, to understand what is the growth mechanism, because we need to know how to control the size of these nanotubes, how to control the number of shells in this multi-walled nanotube, the helicity, that means the chirality and other structural aspects of the nanotubes, how do you control them during synthesis. To know that, we need to understand the mechanism, and in the mechanism what is necessary is the role of the metal catalyst, because it is important. The metal catalyst is important for single walled nanotube growth. Then the size dependent on the carbon nanotube, the diameter length of the carbon nanotube depends on the composition of the catalyst that you use, and the size also depends on the temperature of growth. So, these are various factors on which the size and number shells etcetera, the helicity is controlled. So, the growth mechanism which is very popular is shown here. This is two methods are given, the base growth method and the tip growth method. And in the base growth method, you have the substrate or the support on which you have the metal catalyst. Now, when you add the hydrocarbon, which is the source of the carbon nanotube or the carbon, the hydrocarbon decomposes or vaporizes and gives rise to carbon, and this carbon then forms or reprecipitates on top of the catalyst and then starts growing on top of it on the metal catalyst particle. So, this is the metal catalyst particle, and this the carbon is depositing on the surface, and slowly it will grow along this direction, and then you get the carbon nanotube. This is called the base growth mechanism, because the catalyst remains at the base. The tip growth mechanism is normally shown here. You have the metal and the support, and then when the hydrocarbon decomposes to give carbon and hydrogen, and the carbon is dissolved in the metal particle, then the when it reprecipitates, it precipitates at the bottom, at the tip of this, and not on top of this like it was doing here. So, when the carbon deposits here at the tip, then the catalyst particle moves up. So, the catalyst particle keeps moving up and the carbon nanotube is formed here. This is called the tip growth mechanism, because the carbon nanotube is forming at the tip of the metal particle, the catalyst particle. So, as you see, this is the tip of the catalyst particle and the carbon is precipitating here, and so this tip will continue to move up and the carbon nanotube actually will form on the substrate. The difference in the two, as you see, the nanotube here is on top of the catalyst particle. Here the nanotube is on top of the substrate and the catalyst is on top of the carbon nanotube. So, these are two very different growth mechanisms, the extrusion or root or base growth mechanism. There are various names for the same mechanism. The other mechanism is the tip growth mechanism. The nanotube is growing from the tip. So, this is another way to show the same thing, that you have a metal the transition metal surface here, and the carbon nanotube is forming outside, and is this carbon nanotube is nucleating along the periphery. Now, this is another picture to show you that how the catalyst particle is at the periphery of the tube, and it allows the growth of the nanotube in this direction by hopping from side to side and not allowing the pentagons and heptagons to form, because if the pentagon and heptagon form, then the tube will start getting closed, but if only hexagons form, then the tube will continue to grow. So, the catalyst's key role is not to allow a pentagon to close by forming a bond there temporarily and then moving to another place till a carbon comes and forms a hexagonal ring. So, the catalyst avoids making pentagons and heptagons, and by avoiding formation of pentagon and heptagon, it avoids closure of the tube. So, today we will close here and will continue our lecture for the third lecture of module 3, where we will look at the applications of carbon nanotubes in much more detail. Today what we did is look at the synthesis of carbon nanotubes, the chirality of carbon nanotubes, the various types of catalysts that are used in the nanotube formation, and the growth mechanism of carbon nanotube. Thank you.